Okay, so what we learned last time, there was the Gauss's law, which is the close connections or relies so much on understanding of how you calculated flux. Okay, and once you had that sort of like sought out, and then you are just like extend the idea of flux, that actually the source of all those flux just it's just came from charges. Okay, so that means if you have any evidence showing that you have a net non-zero flux on the surface somewhere, which is supposed to be a closed surface, then that means there must be charge inside that enclosed volume to generate those flux. You got that one? All right. So that seems all right, right? It seems like, okay, that's kind of like it's one-to-one mapping. Whenever you have some flux, sort of like non-zero flux, there must be non-zero charge along with it. And that was the Gauss's law. Okay. Then, so what we have next for you is just how can we make use of that, even though it's not particularly like a direct application per se, but it seems like there is some connections there. So I think this is a good idea to introduce to you the device that's used massively in electronics and or whatever in our everyday life, and that is a capacitor. Okay, and what we are going to learn today is how can we sort of like identify the property of capacitor that we are going to name that property the capacitance. Okay, so as the name implied, it seems like the capacitor is some capacity. So this means it's some sort of like ability to store something. Like think of it like a warehouse or something like that. Okay, so that's what we are trying to do here is we are going to actually have a device that has an ability to store charges. Sounds good? All right. And of course, you can imagine that the bigger the storage, that means the bigger the capacitance. So the name of the capacitance allow you to be able to sort of like classify, or it's not classify, it's like identify, or I mean, it just let you can tell how big is your capacitor or how big is your ability to store charges. Sounds good? All right. Now the concepts, it's actually very easy. All right. So I don't want you to think too complicatedly about this one because the idea is very simple because it's made out of something so simple. Think of it this way. So first, if you have some conducting material. So when I say conducting material, mean is the material that allow those charges inside move very easily. Okay. So the familiar one was just the one that we already mentioned like a couple of weeks ago was this metals. Okay, so you know that electricity can travel inside metals very easily. So those are the things. So that means if you have that type of material, but then in general, those materials are neutral. If you don't do anything with it, they are just neutral. That means you have equal amount of positive charges and negative charges inside that material. Okay, so most of the stuff around us are neutral. Okay, now when you put two of that material side by side, and then somehow, if you are able to look at this figure here, if you somehow can transfer or just transport part of the charge from one to the other, okay, sounds good. So for example, because I mean, most of the stuff that actually can travel easily is electron. So you can imagine that if I can pretty much like move electron from one side to the, I don't have to follow along that line here, but somehow if I can transfer part of the electrons from one piece to another piece. So the conducting piece on the left will turn more positive, hence the positive sign over here. And of course, whatever the positive charge that the left part of, the left piece of the metal get, that means you deposit the same amount of negative charge on the other one. Sounds good? So that means if the left piece is positive Q, the right one must be negative Q. That's all right. And now once you have this, everything go back to things that you have learned before. Now you have distribution of charges. So you have positive on the left, you have negative on the right. Now you can explain this scenario in whatever you like. If you want to talk about electric field, well, no problem. There must be some electric field lines. It's coming out from positive charges and it's gonna ends on a negative charges. Cool. Or you can pick to talk about potential. You already know that. All right. You can always figure out the potential around any charges. So you can probably can tell like around the positive charge, the potential is going to be high, and the negative charge, the potential is going to be low. So that means among these two, there must be some potential difference. Okay, so that's a delta V. Now, this is just a quick note. I don't know why, but when you talk about electricity or currents, or I mean, that's we're going to do next, or some circuits and all this stuff, they don't want to put delta anymore. I don't know why. All right, but just take that as like a maybe just just a quick way of writing, because everyone now understand that you don't have like a absolute potential all the time. Whenever you talk about potential, it must be with respect to some reference. And if you want to use the KQ over R, remember that we said that the reference is at infinity. Okay.
Okay.
All right. But of course, if it is not, then you want to just compare between left and right. I mean, it's going to be some potential difference. But instead of keeping writing the delta all the time, you just drop it and just say V, I guess. That's my guess. All right, so cool. So now I hope you sort of like see that every time you see V in there, that means potential difference. Now, once we have all these components ready, it's time for us to imagine how can we store charge in it. So of course, Ajan, it must be relationship between the amount of charge that you're looking here. So that's the amount of charge. Oh, it's just disappearing it. So that's amount of charge that you can put on those pieces of metals or pieces of conductors. And of course, you just say, if something is going to store like very easily, so it's mean like this system can store a lot of charge, that will go hand in hand with a big amount of potential difference as well. Does that make sense? Okay, so it means if this system can have like a big chunk of positive Q and negative Q, the Q must be the same, of course, right? Because one positive, one negative, but the magnitude of Q are the same on both pieces. So what you have over here is mean the bigger the Q, yeah, the bigger the V. Why not? Because when you have like a lot of differences in charges, that will lead you to a big difference in potential as well. So from the look of it, the common sense seems to lead you to think of the Q must be proportional to the potential difference. And yes, that's what it is. We're going to turn this proportional relationship into an equation. So we need some constant there. And that constant, we're going to call it a capacitance. Sounds good? It's as simple as that.
Okay.
Okay. And why does it so? The reason for this is actually, if you want to look at this one and why you want to call this C to be your capacitance is just because you say, let's say if you fix V, let's say if the V is fixed, okay? So the bigger the C, the bigger the Q. Does that make sense? So, okay, so the C seems to give you an idea of how big the Q should be for one particular value of potential difference. So that's why we're going to name this capital C, the capacitance. Cool. And what is the units of this one? Okay, about that, that's no big deal. You just move things around. So the capacitance is, you can write a formula that looks like this. It's just the charge per volt, but the charge is in Coulomb, volt, charge per volt. I need to clap that. It's charge per potential difference, right? So it's mean the charge has a unit of Coulomb and the potential difference has a unit of volt. So it's a Coulomb per volt. That is the unit of capacitance. And we have a name for it to honor Faraday, all right, who's done a lot of stuff that made us confused today. So we call this unit farad. Okay, so the farad is the unit of capacitance. Cool. All right. And you guys, when I say you have tons of this application of this device, because you probably have spotted this kind of device on maybe electronic stuff or circuit boards or whatever inside your PC, your TV circuits and everything. I mean, every electronics required because you always need something there and come in like different size and shape and all this stuff, but they're all capacitors. Okay. And if you look in here closely, see that? There you go. This one say the capacitance of this one is 4,700. That's a microfarad. The capital F, that's a farad. So actually 1 farad is a huge amount of capacitance. Okay, so usually the capacitor that you use, if it's only in like electronics pieces and other stuff, it comes in like a micro. And if you spot this one, if I can see here, this is even like, this is, I think, I don't know, is it nano or what? But that's what it is, right? It's very small. It's come in a very, very small value of farad. Okay, so it might be showing up as a microfarad, nanofarad, or even down to picofarad, even 10 to the negative 12. All right, so that's pretty much definition of capacitance. It's just a ratio between the charge per potential difference. Easy enough, you think?
Okay.
All right, cool. Now, where does the Gauss law fit into this? So the way to understand this one, eventually it turns out there is a very, very interesting property of these capacitors. So what we are going to learn today is we would like to calculate the capacitance of some particular shape capacitors. Okay, and as I'm showing you at this point is I have the first one, the top one is the easiest. It's just a parallel plates capacitors. That's the easiest one. However, the key is you want 2 pieces all the time, right? Because one is going to turn positive and the other one is going to turn negative, right? So that means every time that you're going to have to deal with capacitor, you have to deal with 2 pieces that come in parallel somehow. So this is going to be the easiest kind. You just 2 parallel plates. One going to be positive, one going to be negative. That's one easy. But the next one that it's also possible is if you would like to keep something in like a spherical shape, then of course you must need like 2 spherical ball. It's not a ball. It's supposed to be a shell. So you need 2 spherical shells. And then of course they are like maybe concentric shells. So they're sharing the common center. And then you have some sort of like a parallel plate, but curled in a spherical shape. Does that make sense? Or even you can take that parallel plate and roll it up if you think of it that way. And once you roll it, you might be able to end up with the cylindrical shape. But as you can see, you always have 2 pieces. One is going to be positive, the other one going to be negative. One positive, one negative. One positive, one negative, all the time. Cool? All right, so what I'm going to show you here right now is how can I actually calculate the capacitance of these 3 configurations or these 3 shapes of capacitors, okay? That's what we're trying to do here. And I break it down into 3 steps, and hopefully it'll make things a lot easier. However, the good thing is, the good news, at the end, this is like a recipe again. It's just like Gauss's law or something like that, even though, I mean, at first it looks complicated, but at the end, the final result is just like, it's always like this, okay? So it's just like you just sit back and relax and just listen to my talking about how to calculate the capacitance. And once you're done, you can just, look at the final results and okay, just nod your head and then, okay, it's not too bad. All right, but anyway, I will have one question in the exam talking about this, and I want you to try that one in the exam paper. So that means it's like I'm telling you what is going to be the question in the final exam somehow, right? One of them at least. Okay. All right. So I break it down into 3 steps. Following these 3 steps, you're going to get the C calculated. First, you need electric fields. Second, from the field that you got from this, allow you to calculate the potential difference. Once you have that, potential difference eventually will lead you to ability to calculate the ratio between the charge per unit volt. You are done. So, all right, so that's a 3-step process that we're going to do. Okay, and I'm going to show you slowly how this thing can be done. But before we get to that, I think this is a good place because, I mean, I can go further and further and talk about how to calculate that right now. But I think this is a good place for you. Once again, guys, if you could go to the website, once again, theallphysics.com. Okay, try that. And then you look at the E&M and you look at the capacitor lab. So let me give you the link here again. There you go. All right. So if you guys want to check this one out, that would be great. All right. But once again, for those of you, this is take a look at the video playback. Then you can just go to Office. Okay, let me share the screen here. All right, here we go. All right. There, where is my screen? There you go. There. Already. That's what you have here. Okay, so you can see over here that this will give you some simulation for fun. Again, this is the easiest type of parallel plate, easiest type of capacitor, which is a parallel plate capacitor. And what you can do is you can show electric field, okay, and you can change the plate area a little bit. You can change the voltage across. You can change the resistance that eventually going to have a chance to calculate that. All right. And then you can also change the distance between the plate. Okay. So there are a couple of parameters that you can adjust. All right. And what you have is close the switch. See that? So, I mean, we are going eventually to about to calculate this dynamics that's going on over here. But at first, you can see that there are arrows pointing down. The reason is because if you remember, we're going to look further into this, but on the right side, that's a battery. So you see you have 4.6 volt applying to this parallel plates capacitor. So the top plates turn positive while the bottom plates turn negative. So this is the reason why there will be a downward electric field. Cool. All right. Now, if I open the switch and I reduce the voltage. All right. But anyway, this is just my way of doing it. They might not allow me to do it, but that's okay. All right. See, there will be some dynamics going on over here. But because right now we don't have the detail that's going on about the dynamics just yet. We're going to learn this next week. All right. But for now, what I can do is this process of putting the charge on it. And once the charge is on it, you're going to get the electric field. Of course, electric field come with the electric potential. Everything come in a full package, right? We learned from a couple of weeks in the past. So that's what is happening in a capacitor. Cool. All right. And you have a button over here on the left there that called Discharge Capacitor. So that means I want to just get rid of everything, start all over again. So let me do it one more time. It doesn't have like a slow-mo version of this, but let's give it a shot. So right now it's blank. So these two plates are neutral, 0. So once I close down the switch, there will be a charge flow. It's an electron flow from the upper plate to the bottom one. So the bottom one will be more negative. The upper one will be more positive. So let's try it again. Close the switch. Bam. Here we go. So you start accumulation of a positive charge on top, negative charge in the bottom. So you gain more and more electric field. Once the electric field is getting bigger, the potential is going to grow bigger as well, on and on. Okay. Does that help?
Okay.
All right. And as you can see, the number is still running. So even though the animation is already stopped, but actually the calculation moves on because I think the change is very minimal. And next week, you will have a chance to learn this. What is the change of this number? What kind of function, the mathematical description of this? Okay. It's going to be a lot of fun. And it's going to be calculus, of course. Yeah. Okay, guys. So that's very cool. And once again, I still recommend if you want, I don't know, are there any? No, I think that's the only capacitor animation that they have, but that's all right. I think you have enough idea what's going on. And of course, if you have different shapes, like you saw before in a spherical or cylindrical, concepts stay almost the same. Okay. You will generate charge accumulation. Those accumulation of charge will generate the field between, and the field in between indicates that there are some potential difference. That's it. Okay. All right. Come back to our slide and see what else do we have for you here. You guys still having fun, I hope. I know you guys must be very, very tired right now. That's why. I don't know. Will there be anybody next week? Oh, I understand. Even it's just like I'm tired as well. It's a long trimester. I can feel we have to fight so many fronts at this point. So many things going on. Okay, guys. So first thing first, step number 1, I want electric field. See, because we already saw it. When you start to accumulate charge, positive on top, I mean, it could be top or bottom, but over here they said it's on top. And you have a negative charge accumulated in the bottom plate. You are going to develop electric field in between. Cool? All right. First step, I want to know what is this E right here? Hey, what is this? I want this. How can we figure out electric field in between plates? Okay, that's step number one. So let's take a look at this. So seeing this, all right, so this is the sort of like a zoom in version of that one. That is a positive side of things. So I'm looking at the positive charge over here. So here comes the Gauss's law, guys. All right, last time you only did the Gauss's law in a spherical setting. Now we have difference. You can see that the charge is now in a sheet. See on the left, it's like a big sheet of charge. It's like you think of it like you have like a super huge paper, and those paper you have charges deposits on it. Cool. So that green big piece of stuff, that is just like a big sheet of charge. Now you are standing in front of that piece of paper, a charged paper. The question is, what is the electric field at your position? What do you think? All right, so this is going to be a tough one. If you haven't done this before, it's going to be like take some time for you to think of how can you calculate electric field using Gauss's law. But you might just ask him, Ajahn, can we not using Gauss's law? Well, yeah, you can. But if you're not using the Gauss's law, that means you're going to have to slide this into a tiny piece called dq, just like before. And then at the position that you're standing here, that dq will generate dE vector. And then you move on to the next one, it will generate another dE there, move on to the next one, generate another dE there. And then you have to keep doing this. So there'll be like tons of the electric field from everywhere on this sheet of charge that you have to sum. Can we do it? Yes, we can. But it's going to take you a lot of time because it's, wow, I would say it's a double integral in the vector quantity. So it's, once again, vector calculus for sure. But now you're going to have to do the vector summation from the two-dimensional integral. No, that's not easy. All right. So what we're going to do is we're not going to try to do this calculation using Coulomb's law. That's way too complicated. But because now you have a sheet of charge, it's highly symmetric. You see what I'm saying? It's highly symmetric. It's highly symmetric. So if you look at the side view, guys, so the side view will look like this. So let me put like a highlight over there. That's a side view. So I'm looking here, side view. Okay. So when you look side view, there is a charge deposit on the surface of this metal plate or whatever material that you use to make the capacitor. So when you look at this one, it's highly symmetric because it's just like a flat line when you look edge on. When you look side view, it's just like a flat line, right? Even though it's extended infinitely. Okay. And it has like some sort of like a symmetry on the left and on the right. That's nice. Okay. So at least this is not bad. From this symmetry alone, it seems like the electric field supposed to go out in all direction, left and right. So let me sort of draw like a highlight something like this first. So it's supposed to go out like this. You guys can imagine that? Just from the piece of charge lying in the flat paper, electric field is supposed to point out perpendicularly, assuming that your paper is huge. The reason for this is because imagine if you're standing here in front of this big paper, you're standing over here, you look up, you don't see the edge of the paper. You look left, you don't see the edge of the paper. No edge. It's like you're standing at the sea and you cannot see the ends of the ocean, stuff like that.
Okay.
Does that make sense? So it's like the surface of the ocean is like an infinite, super big piece of water or whatever. It's huge. Okay. And let's imagine that surface generate electric field towards you. So when you look around you, okay, they all cancel each other out horizontally if you're just floating on the surface of the ocean. That will be the only single direction that doesn't have any cancellation is when you look up. You see the sky. Does that make sense? So when you see the sky, there's nothing else to cancel this one. All right. So what I'm going to show you is this, just to imagine this. The charge over here will generate the field down. Charge over here will generate the field down here. Charge over here will generate a field down there. Charge over here generate a field here, on and on, right? I'll just keep writing, keep drawing, keep drawing. See? So when you look at this one, it has a symmetry up and down. So what I'm saying is you can cut this in half. There will be equal amount of vector pointing up and equal amount of vector pointing down. So that means the vertical components of the vector will cancel themselves out. Cool?
Okay.
That will be the only component that cannot cancel. It's the one that actually point to your right. So that's why I'm saying I can now undo this whole writing here. So what I'm saying over here is when you have like a very, very infinitely extended two-dimensional sheet of charge, the electric field that coming out of it supposed to be just straight out, straight out, straight out, straight out. Cool? Let's make it very easy. All right. So guys, this is probably the hardest part of the course, I would say, because imagination has to be in here too. All right. But then, remember last time, guys, we said every time that we have like a cage of charged material, I mean, if you have like a cage that is charged, there will be no electric field inside. Remember that? We did that last time. And this is what happened here. When you have a conducting material, just like metal, it turns out those charge will eventually accumulate on the surface of the metal, not inside, because everything gonna get pushed away until it sort of like back against the wall of the surface of the metal. So that means you are talking about a metal piece that has a cage on it. I don't know if you guys follow idea or not. So let me redo it one more time, guys. So this one is important in the sense that if you understand it once, then you don't have any question later. So think about this. In reality, the piece of metal will look something like this. So let me draw it like a huge one here. So this is a piece of metal right there. And now let's assume that you spread the positive charge on this. And of course, when you do it at first, it might not distribute it yet. You might just want to like throw them in here on just that upper right corner. Just like, okay, I throw a bunch of charge on there. And this is just a piece of metal, right? A solid piece of metal. So what will it happen to these charges, guys? What do you think? So it turns out these charges eventually will redistribute themselves. And it will end up only on the surface of the material. Why? The reason is because if you have some charge still inside, the Coulomb's law will come into effect because the same charge will repel themselves or they repel each other. So that means whatever charge that's floating in space, in the inner portion of the material, eventually will get pushed and pulled or whatever. And everything will eventually stop when you guys are against the wall. You guys with me with this imagination here? Imagine this. If you come into a classroom and let's say you guys are all electrons, okay? So that means you cannot get close to your friends because whenever you get close to your friends, you get Coulomb's repulsion, right? You're gonna get bounce each other. So you're gonna keep bouncing against each other because you guys cannot stay close. But at the end, you're gonna stop somewhere. Where are you gonna stop? What do you think? Yeah, the answer is you're gonna stop on the wall. Maybe on the ground or on the ceiling, doesn't matter, but your back must be against some surface of the room. That's when you're gonna be able to stop. Does that make sense? Okay.
Okay.
Because if you come into the center of the room, you're gonna get some Coulomb repulsion or whatever, and then eventually you're gonna get stuck back into some walls or some surfaces, whatever. So that means at the end, all those charges will be resides on the surface. So once we have this, hence what you get here, guys? Yeah, that is the cage. The piece of that conducting material behave like a cage. So that's why we say electric field is supposed to be zero inside. So now that's the end of it. You only have electric field coming out at one side of this, which is away from the metal itself. Cool? And that's why this figure over here, now I can erase my sort of like crazy drawing over here. That's it. I hope you understand this figure over here. All right. I mean, I might spend a little bit too much time on this one, but I hope without doing the detailed analysis of this drawing, you might be confusing like why the electric field is 0 on the left, well, and why electric field is supposed to go horizontally only. There's some reason behind it, and that was what what it was there. Okay. All right, guys, that's very good. So that's the conclusion. Before we haven't done any Gauss's law yet, but that's the conclusion that this is the scenario that we have. Come back to our main goal. The goal of us is we want to calculate the electric field here. How much is the electric field a little bit away from the metal plates? Here comes the Gauss's law. Now you already know that electric field has a horizontal sort of like, direction, symmetric, up and down, everything is good. Now is your turn to come up with a Gaussian surface, guys. What do you think is the shape of the Gaussian surface should be? That allow you to calculate flux very easily. Come to think of it, Ajan, well, it's not going to be a sphere anymore because there's no spherical shape whatsoever in this figure here. But then think about it. It's come in like a sort of like a horizontal piece. Then if I cut this perpendicularly, this is the one that we love, right? We have done a couple of exercises. So this is something that nice. So I'm going to pick like maybe like a box here. Okay, let me put in the green here. So I'm going to put a little bit of perspective in there. It's just not good. All right. Let me do like edge on. So if I put a box here, does that make sense? Or I could put like a cylindrical shape stuff. It doesn't have to be like a cubical box, or it doesn't have to be a rectangular box. It could be like a cylindrical shape stuff. But what I want is I want something that's oriented along the horizontal direction with the cross section that's perpendicular to it. So that why we came back to this figure. Now I hope you understand this perspective over here. So as you can see, I don't need to pick a rectangular surface. It could be a circle here, or it could be like a square here. Okay, doesn't matter. Any figure, any shape of the surface will do. But the point is, you want things to look like a cylinder over here with cross section. So when you look edge on, it will look like this. And the front surface, let me highlight green here. That's your front surface there. That is this front surface here. And the back surface there, let me highlight blue. That is your black surface here. Cool. The reason that we want this one is because I think now you understand why. Let me ask you, just like what we asked before, what is the net flux on this piece of Gaussian surface? Guys, well, then we know this already. First thing first, there will be no flux on the side surface. With me? Because electric field only runs horizontally. So of course, there's no flux through the side surface. Now, only the green one that seems to have some effect of the flux, because the area vector on the green surface, let me highlight green as well here, is going to point out perpendicular to the actual surface. And this is parallel to the E. Perfect. So that means flux on this surface, let me call flux on the right surface here, is going to be E dot A on the right. And it's just size of the E, size of the A on the right, cosine 0. And that is just E times A on the right. And you are done. That is the flux through the green surface there. Very nice. Almost done.
Okay.
What about the blue? But on the blue, you don't even have to calculate it. You can call this flux on the left. It's definitely 0 because we already concluded that there's no electric field inside. See? And that's it, guys. The net flux on this Gaussian surface that we built is just give you flux. Oops, sorry. Okay, flux on the top, flux on the side, and well, we call top, bottom. I think it's supposed to call left and right. The orientation is not vertical. So, okay, let me call left and right. So the flux on the left, flux on the side, and flux on the right. Side 0, left also 0. This one go to EA on the right side. See, so you already knew what is going on the left side of the Gauss's law equation. The only thing left for you is you just have to equate to the amount of charge inside this Gaussian surface, and then all you need to do is just divide it by epsilon naught, right? And you will be almost done here. How much charge on here, guys? Don't think too much. You only care about the charge that is inside this closed surface. That's it. Because this closed surface only cover that circular portion of this sheet of charge right there. So let me refer to you to use sigma now. So sigma is the charge per area, right? Now we complete the whole density in all dimensions. One dimension, we have lambda, charge per length. 3 dimension, we saw before, we have rho, charge per volume. Now we have 2 dimension, we have charge per area, we call it a sigma. So the good thing about defining the sigma is you can say that the amount of charge that is enclosed within this closed surface is going to be just sigma times the cross-sectional area over here. And that's it. So that's good. So this is going to be sigma times the cross-sectional area. However, it's the same cross-sectional area here. Same thing. So it's a A times R, guys. So let me draw this equation one more time. It looks like EA on the right equal to sigma A on the right over epsilon naught. That A cancel, and hence this, that's it, done.
Okay.
Isn't that cool? The cool thing of this one is now you already figure out the electric field without doing any like crazy vector calculus and all this stuff. No need to do the Coulomb's law, calculating the distance and just square them, put them in the KQ over R squared, sum them vector format, on crazy stuff. You only use the symmetry argument that's already inherent in the Gauss's law. And that's allow you to figure out the electric field right away. And the final result is so cool. See? Do you notice something here? Electric field is going to be exactly the same no matter where you are. There's no distance in this equation. Nothing. So it means you can stand here, you can stand there, you can stand here, there. Doesn't matter as long as you stand in front of this metal plates with the charge density sigma, you're going to get the same amount of electric field, sigma over epsilon naught, and you are done.
Okay.
Okay? The electric field is constant everywhere and point horizontal, perpendicular to the surface of the conducting metal. Okay, cool. All right, so I hope you see how can we, well, you can think of this one as like a problem of the Gauss's law directly if you want to, but then what I really like is I'm just gonna sort of like drag you further because you already know how to figure out the electric field here. Why don't we just doing the capacitance right away? So that's what we're gonna do next. So once we have that, okay, so conclusion over here is easy now, sigma over epsilon naught, that's your electric field, right? Then, here we go. All right, so that's step number 1 is done. See, so the step number 1, find the electric field using Gauss's law. And that's exactly what we need. But Ajahn, why don't you care about the negative plate? No problem. You can actually do this whole thing on the negative plate as well. It won't change anything. It will look exactly the same. So this means you're going to end up with another side of this whole thing, right? Another plate. And that plate will have like a lot of negative charge on it. That's okay. But anyway, the argument stays the same. So it's means electric field just going to come here and then just ends on that negative plate. You can do equally well by doing the Gaussian surface on the negative side as well, but it's just flipping the sign. So at the end, what you get is going to be the same result. The electric field in between these plates is still sigma over epsilon naught. Got that one? Cool.
Okay.
All right then. So that's a step number 1. That's done. Now you know the field you should know the potential difference. Remember that, right? When we go against the field, we go into a higher potential. If we go along the field, we're going in the same direction as the field. We're going to a lower potential, right? So we already got the conclusion that every time you got the electric field, it means you will be able to evaluate the potential difference. And the relationship is going to be according to this equation over here. However, for our purpose, I mean, not our purpose, our setup over here is very simple. Electric field is constant. So electric field over here, E, is constant. So when you want to do this integral over here, it turns out into just a simple integral of E ds. And now the ds is just a distance that you want to go from upper plate to a lower plate, a lower plate to an upper plate. Because we want everything to be positive, so that's why what I can do is I can walk from the negative plate and walk up along the green path up to the positive plate. And that would be my ds. So my ds is just a tiny vector along that green line there. So that's my ds over here. So what you have over here, as you can see, electric field is coming down, the ds is going up. So you want to do the integration from that, give you cosine of 180 degree. Isn't that cool? All right, next. What you have here is cosine 180 give you -1, negative turn meet with the negative turns positive. So it's going to be integral of E ds. E is constant. You are left with just the integral of the ds, but the integral of the ds is just the distance over here because you just take ds, 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 and sum them up. You just get the distance between the plates. So it's just ED. But then, John, this is what is the formula that we already got last time. Remember, when we talk about the relationship between the potential and electric fields, you have two types of problems. Either you have already known the electric fields or you have distribution of charges. And this is the first type. You already got the field, multiply by the distance, you get the potential difference. So perfect, ED, that is done.
Okay.
Okay. So once again, this problem is just like MGH, just like we already discussed this back in the day of potential. Okay. All right. So now that is the potential difference between the positive plates and the negative plates. The last step is the easiest one. So step number 2 is done. You already calculated potential from the field. The last step is the easiest. The capacitance is just the charge per potential difference that you got from step 2. So I'm just take that, plug it in here. So what I'm getting is going to be Q over E times D. But E, we got it from the first step. Okay, let me write on here. E is sigma over epsilon naught. So I just plug in the E here. So it's just going to be equal to Q over sigma. And then I just flip the epsilon naught on top and over D. Okay, isn't that cool? All right, and what you have over here is, whoa, something is missing here. Wait a second. Okay, V equal to E times D, E times D, and you have a Q. Yeah, okay, that's done. Okay, that's good. So, however, the sigma that you got before was just a charge per unit area. Okay, sorry, I thought I wrote it incorrectly. So the sigma over here is just the charge per unit surface area, right? Charge per area. So I can turn this into, okay, follow my green ink over here. It's charge per area with the D. Almost done, guys. Bear with me here. Q cancel. So now Q is out of the picture. I flip the A to the top, divided by D. And that's it, guys. You are done. Whew.
Okay. Okay.
It seems long at first. However, what you're seeing over here is just a 3 steps process. Get the E from the Gauss's law. Once you know the E, the field can be calculated using the relationship between the field and the potential difference. Don't forget the negative sign, as we already mentioned before. And once we have that, then you just take the potential difference that you got, right, into the definition of the capacitance. It's a charge per potential difference. And you just rearrange form whatever you got a little bit. You take the electric field from the step 1, put it in step 2, get the delta V from the step 2, put it in step 3. Q eventually cancel, and you get the end result that look like this. You are done.
Okay.
So that is the capacitance of a parallel plate capacitor, having the charge, having the plate, this plate area A, and the distance between plates D. We'll come back after the break and we will discuss the property of this once we already found out the form of the capacitance. Sounds like a good plan? All right, guys. So let's take a break here.
Okay.
All right. So what we learned from this expression is very good. First thing first, charge is not in the figure here. It's not in the picture right now, which makes sense because what we want for the C is to be the property of the capacitor. So it shouldn't matter if it's like having a charge on it, when, where, and it doesn't matter. I just want to have like some characteristic of the C. So that's why the conclusion that you can draw from this one is it depends on the physical shape of the capacitor. Does that make sense? So it just depends on how big is the plate or how far away is the plate between the plates. That's it. It's just the shape of the capacitor itself that determines the size of the capacitance, which is very good. Okay. So by having that, so you can probably start to guess like, hey, other capacitors should have the same kind of stuff. So it means to be able to imagine or to be able to tell how big, how small of the capacitance or the ability for that capacitor to store charges, you only need to look at the shape of it. Does that make sense? All right. So what we are going to do is we're going to show you one more. Okay, one more of the capacitance calculation in the different shape of capacitor, which is going to be spherical. But once we're done with this, I hope you understand how the touch screen works from your whatever smartphone or tablet or whatever, right? So that's using the capacitance property of some devices inside the display. Okay, but before we get to that conclusion, let's do one more, shall we? All right, and after this one, I'm going to tell you what will be the question in the final exam. One question that you guys definitely have to do it because I'm telling you what is supposed to show up. All right, guys. So take a look at this one. Now, instead of having two parallel plates capacitor, now you have a two concentric spheres. Okay, but of course they are conducting. So you have two conducting spheres sharing the common center. One is supposed to go positive, the other one go negative when you charge it. All right. So when you charge, mean you transfer charge from one piece to another piece. Yeah. So let's assume that the inner sphere has a positive charge plus Q. Okay. And the outer sphere has a negative charge minus Q. Cool. So that meets our condition right here. So we're going to go through 3 steps process just like before. Why not? All right. First, I would like to calculate the electric field between these concentric spheres. I said between plates, but well, it's not a straight plate anymore. It's curved. All right. So first thing first, you should be able to imagine that, well, Ajahn, the electric field go from positive to negative. So from the look of this one, now we have spherical symmetry. Cool.
Okay.
All right. So that means electric field is supposed to go out. Okay. Let me sort of like put a faint electric field. Oh, that's too faint there. Sorry. Yeah. Electric field is supposed to go out, radially outward, radially outward, radially outward. There you go. And it's supposed to start from positive charge and ends on a negative charge. So perfect. It looks radial, so radially outward. So the Gauss's law allow you to calculate the fields in between very easily by picking the Gaussian surface to be a sphere as well. So I'm going to draw a sphere wrapping the inner sphere. So it has a size somewhere in between. And then we are going to figure out the flux on this Gaussian surface. So this is your Gaussian surface in the form of a sphere. Cool. All right. And we follow the same things that we have done 5 times last time. Okay, so on this surface, the surface area vector is going to point in the radial direction. Electric field, we already concluded, is point in the radial direction as well. So what you have here is the flux on this one. You can call it just the integral on this closed Gaussian surface here, and E dot with the dA. Cool. But because E and dA are parallel to each other, so it's going to be E dA cosine 0. And because E by spherical symmetry,
Okay.
you shouldn't have any electric field in some particular directions stronger than some other directions. So electric field is supposed to have the same magnitude everywhere on this surface. Okay, so I can pull that E out from the integral, and you have only the integral of that tiny dA across this sphere, the Gaussian sphere. And that is just 4 pi r squared. And the r is just going to be the radius of this Gaussian sphere. That is the 6th time you're seeing this. So this is the electric field, the flux going through the Gaussian sphere right here. And now you only equate this with the charge that inside this sphere divided by epsilon naught. How much is the charge you're going to put here? Well, of course, Ajahn, you saw positive Q there, you just put positive Q here. Done. Or actually, without doing this, but Ajahn, I thought you talked like about spherical stuff. If you stay away from some spherical distributed charge, you're going to get everything look like a Coulomb's law, right? And this is exactly what it is. So if we move everything to the right side, you're going to get 1 over 4 pi epsilon naught capital Q over r squared. Once again.
Okay.
Why not? All right. So what I'm saying over here is because you still have spherical symmetry over here. I mean, when I say not only that, because you have like a positive Q at the center. So away from that, you're still supposed to get electric field in the shape of, electric, in the shape of Coulomb's law anyway. Okay. However, the difference is if you grow bigger, if you come out, if I'm asking you just for fun, what is the electric field outside this capacitor? Okay, and first, what we're looking at is at the inner sphere is not like a solid sphere, it's a shell. So everyone should be able to tell right away, but John, that's nice. Electric field here is supposed to be 0 because it's a shell. We already understood it. You have like a cage. So when you have a charge sort of like gather in the form of like a cage, if it's a shell, electric field inside is 0. And same thing with the outside, electric field outside over here is supposed to be 0 as well. Why? Because you look into inner volume of this outer sphere. Do you see the net charge there? It's positive Q and negative Q. So when you do the Gauss's law, the charge included turns out to be 0. So perfect. So in conclusion, for this particular capacitance, the scenario looks very familiar, just like what we had over here in the parallel plates case. So you have inner sphere, you have an outer sphere, which is they're all spherical shells. You only generate electric field in between these two spheres. That's it. And the space around this capacitor, we can assume that electric field are 0. Cool?
Okay.
Nice. It's sort of like a self-contained. So it's like you have positive plates, you have negative plate, and the electric field just going in between. It's contained within that region. There's no other place that have electric fields. Cool? All right. So that gives you an overview of what does it mean by, electric field outside, inside, and in between. Yeah. All right, cool. Now that's done. Step number 1, you already found the electric field between two spherical shells over here. Step number 2, now we need to do the calculations of the potential difference. So you want to walk from, we want to walk from negative to positive charge again, if you want. So what you want is you want the delta V here, right? Which is the same as V, just notation. So what you want is just the potential difference between the negative sphere and the positive sphere. Now, this is the portion that I think you guys are going to get confused the most if you follow the textbook. The reason is because you are doing the vector in the spherical coordinates. And I think you guys haven't done much of that. So what I'm going to suggest you to do is, well, just do it outward. So that means I'm going to walk from initial point from the positive charge sphere to a negatively charged sphere. So I want to walk outward by knowing in your head, walking in this direction going to give you the negative potential difference. You guys with me?
Okay.
Because you're walking from positive to negative one. So you're going from high to low. So the result, the potential difference is supposed to be negative because you're going to a lower potential. All right. But the reason that I picked the outward direction because things will go a lot easier because everything go in the same direction. Right. But if you go from the negative plate to the negative sphere to a positive sphere, well, you might get the final result nice and tidy to be positive, but I mean, you're going to get confused about the direction, about the radial direction, on and on. So I don't want you to worry about that at this point. So let's do that. So I'm going to walk from inner sphere to the outer sphere. So your ds go in the radial direction outward. Electric field also point in the same direction radially outward. So the E dot ds, they are parallel. So you can calculate the potential difference is just going to be minus, don't forget the minus sign, integral E dot ds. And it's going to be integral with the minus sign, E ds cosine 0. Cool? You're just walking outward, right? ds and E are parallel to each other. And because E, you already figured out from the previous step number 1, which is just the Coulomb's law, K Q over R square ds. Ooh, nice. It's just dr. Why not, right?
Okay.
It's just the radial change, the change in the radial distance. So I can turn this into dr. Cosine 0 is definitely 1. You're going from where? You're going from the initial point, the radius r equal to a. You end at the outer sphere with the radius given to be b. This is the integral that you want to do. Okay. And we still have the negative sign there. That is fine. Cool. All right. This is an easy integral to do because, all right, let me pull a common factor out. It's not a common factor, it's just a constant. Okay. Let me pull constant out. I pull out the q, pull out the 4 pi epsilon naught and everything come out. You only have to integrate 1 over r square dr from a to b. And that will give you, okay, simple minus 1 over r from a to b. Nice. And that's it, guys. So I still keep the negative sign because we kind of know that the final result is supposed to be negative. And then what you have there, you just substitute the upper limit and lower limit in there. So it's going to be 1 over a minus 1 over b. And you are pretty much done on the second step.
Okay.
Isn't that nice? That's not too bad. And I think this is a very good exercise in sort of like applying the relationship between the fields and the potential difference. Yeah. So this is like a very good applications of this particular expression over here. Okay. Very nice. So this is, it's kind of like all inclusive. Like you learn from, a couple of weeks ago and then you apply it here to evaluate some other things. That's kind of like very useful here. All right, guys. So forget about that negative sign. The reason is because we know the final result is supposed to be negative. So the potential difference is supposed to be this number right here. Okay, that is your delta V, or that's just the V that we want to talk about. Now, the last step is going to be the easiest one because you already found out the potential difference. So the last step will go with C equal to Q over delta V. And as you can see, once again, the Q will eventually cancel. So Q over Q, and then the 4 pi epsilon just flip up to the top. Okay, and now you have 1 over A plus 1 over B down here. There you go. All right, and if you rearrange, Q cancel, eventually you get this final equation describing the capacitance of this spherical capacitor, and you are done.
Okay.
Do you see what I see here? Notice this. The capacitance depends on what? See, it's just depending on the radius of the inner and outer sphere. So that's the same conclusion that we had with the parallel plates capacitor. The capacitance depends on the shape, the physical shape of the capacitor. So in this one, it depends on how you pick this ratio or whatever the size of the spheres that will determine the size of the capacitor. Okay.
Okay.
All right. Very nice. So I hope these two exercises, and I think maybe this is the only two examples in the textbook anyway, that allow you to see how can you determine the capacitor of now, first one, the parallel plates capacitor. Second one is spherical capacitor. Now, the third one, and this is the one that I want you to do it yourself. However, not only do it just for understanding, but do it for some, I don't know, some grade, I guess. Get some points out of this. So this will be the final exam question, one of them. Wow. So that means in the final exam, I'm going to ask you to figure out the capacitance of a cylindrical capacitor. All right. So that means this is sort of like a take-home exam or something like I'll tell you right now. So apply the Gauss's law that we done. You haven't done this shape before, but I hope you will have a chance to sort of dig into the textbook or try it yourself, figure out what kind of shape of the Gaussian surface supposed to pick, calculate the electric field out of it, and then use that field to calculate the potential difference like before, almost the same. Once you get that delta V from the second step, the last step allow you to calculate the capacitance of this cylindrical capacitor. Cool? So that means the question in the final will be like verify that you get this expression from Gauss's law, something like that. But when you look at this expression, you see, well, Ajahn, yeah, it's confirmed. The capacitance of this type of capacitor depends on, once again, the shape of the capacitor. See? It just how tall is this or how long is this capacitor? What is the outer radius of the cylinder? What is the inner radius of the cylinder? That's it. All right. There is a log in there. So you assume that there must be some calculus involved, I guess. For sure. All right, guys. Sounds like a good plan. So I'm going to ask you to sort of like show me how can you calculate the capacitance of a cylindrical capacitor in our exam. So I'm just give you sort of like one big question in the exam. So that should be very, very good. All right, guys. So I think this is a good place to stop because that's the end of this handout. And I don't think we want to go too far from this. And I think you need a little bit of time to think about this one and have everything sort of like, crystallize in your head first. And next time, we're going to add on top of this the actual things that you really, really want to do. But to end this lecture, I just want to have you get some sort of like relatable experience. See, the reason that I focus so much or emphasize so much about the property of the C depends only on the physical shape of the capacitor is because of this. I don't know, back in the day that you watched your TV using the antenna, like the Nuot Kung, yeah? The one. And then sometimes when you don't have any clear picture, you have to adjust that antenna. So it seems like you have, if you done this before, when you touch the antenna, maybe the picture looks nice. And when you let it go, it's failed again. I mean, it just go blurred again. And that's because when you touch and not touch it, that is the change in the physical stuff, the physical shape of the antenna. So it's mean antenna with the hands on and antenna without the hands on are having different capacitance. Does that make sense? So that's why, okay, maybe with your hands, it's kind of like you got the clear everything on TV. Everything is on TV is clear, but when once you let it go, it might just disappear. Or even you just walk passing the TV, it might give some weird like flicker of the image and all the stuff. Okay, So that is the property of the C. And then it translates to today's technology, which is a touch screen on your smartphone. So on a smartphone, you have a matrix or whatever, like a mini lines of conducting material, and then you can put them in a crosshair type manner. So it means you have like an upper one and you have a lower one. So at the intersection between those two, it behaves like a parallel plate capacitor. So you see, so there must be some capacitance in between. And once again, with your finger on and not on, it will have the different value of the C, the capacitance. And that allows the chipset inside to determine the location of your fingers on your display. Okay, so that's kind of very cool. And I think Apple came up with this, and that's why you got like a multi-touch screen on it in the first iPhone. Back in the day, before that, I don't know, did you do the Nintendo DS before? They must have like a pen, right? You use the pen with the Nintendo DS, and then when you press on it, you will see that the screen of the Nintendo there, it's pretty soft, and that they use the resistance. We're going to learn about resistance later, but I think you probably have learned about that already. But the reason that you want it to be soft, because you want the pressure to push on it, and that dents into that soft surface of the display, allow the resistance to change. And that's the bad thing about that one, is because you cannot use glass. You need something that is flexible. So that's why the Nintendo's DS screen is supposed to be made from plastic or some flexible material, like polymer and stuff like that. And that is not as clear as glass. Yeah, glass is always better. All right. So that's where, when you look at the specification on your smartphone, it's a capacitive touch screen. And the adjective capacitive is because of this. You use capacitance properties on your display. The more simple one, I mean, the simpler one, the more sort of like a primitive example of the capacitance is just your keyboard. So your display is just like a very complex, sort of like enhanced version of your keyboard. So your keyboard, of course, there's a key. So if you look inside that keyboard, you have a parallel plate as well. So every time you press the key, you just change the distance of that keyboard, or I mean the plate beneath that key. So that means you just change the capacitance of that key, and that allows the computer to know which key that you just pressed. Okay, so that's why, I mean, keyboard don't need any electricity or anything, because all that the board, all that the PC just detects, it's just detecting the change in the C. So, all right, of course, except you use like a Bluetooth keyboard or whatever, you still have to use like some batteries. But just a regular keyboard, you just plug in into your whatever you want, that PS2 or USB, and then bam, it's used very, very minimal amounts of electricity, right? Just for detecting the change of the capacitance on the key. That's all you care about. Okay, cool. All right. So, and that is a clear indicator that every time that you press a key, you change this value right here, the value D over here, that's you changing. Okay. And once you press it, D is decreased, the capacitance shoot up, and now the computer knows which one you pressed. That's it. Cool. All right, guys. So this is a very easy applications of capacitance. And of course, there'll be a lot more. I mean, if you use it in electronic circuits and other stuff, we'll have a chance to look at a simple circuit having the capacitance in the circuits next week. Okay. And that will be sort of like final material that we're going to study in this course. All right. So that will be a lot of fun there with a little bit of differential calculus for you. Okay. All right, guys. So I think this is pretty much it for today. Sounds like a good plan here. Okay, let's draw the line here. We're done. And next time we move on to the next topic in the next handout. All right, guys. That is it for today. And any questions? All right. If not, then thank you very much. And I'll see you guys next week. Okay, bye-bye.